graduate students at Western University. I'm your host, Reese Patterson.
And I'm your co-host, Yusuf. And today we are here with Stephen Pillar, who is from the Geology Department. So welcome, Stephen.
Thank you. Thank you for having me.
So the first question that we're going to ask you is, tell us a little bit about yourself and your research.
Well, I'm a first year's master's student, as you said, in the Department of Geology here at Western. I also did my undergraduate here, and my research is working with fluid inclusions inside rocks. So basically little tiny pockets of gas or fluid, that's any kind of fluid that's trapped inside a mineral or a rock. And I'm using nuclear magnetic resonance spectroscopy to try and evaluate the compositions and the internal pressure of it.
Cool. So Stephen, tell us how you got interested first in, say, chemistry, and then you moved on into, well, examining and imaging rocks in geology. So tell us a bit about your journey from your undergrad to graduate studies.
Yeah, for sure. It was a weird little journey that it took. So I actually came into university from high school planning on taking physics. And after my first year, I realized that definitely wasn't the course I wanted to take, but I actually really enjoyed chemistry. So I decided to major in chemistry throughout my first 4 years at Western, and also taking a major in psychology. But in my fourth year, I met up with my now current supervisor, Roberta Fleming, actually, whether or not she wants me to say that, at a bar one night, and we got to talking, and yeah, so she learned that I had my background in chemistry and I was planning on graduating, but I had no idea what I'd do with my life. So having a background in chemistry herself, Robbie actually asked me, hey, would you be interested in doing a master's here with me? A lot of my research is pretty heavy on chemistry. And at the time, I wasn't sure if she was entirely serious, but I touched base. I sent her an email a little bit later on, and we had a couple meetings and discussed a couple of possible projects and worked it all out. So I submitted my application for a graduate program in the field of geology. I actually ended up taking an extra year in undergrad. I took a fifth year and took an entire minor in geology that year.
Good job.
Yeah, so I ended up graduating with a major chemistry, minor psychology, minor in geology. So got a little something. At least I actually made use out of my fifth year, right?
Exactly. So I have a geology background, obviously. I'm in the same department as you. But what type of minerals are you looking at with the fluid inclusions?
So right now we're not looking at anything too fancy. It's mostly just halites, because obviously there's always going to be fluid involved with their formation. So you have a good knowledge of what the fluid inclusions have. That, and they're really, really simplistic chemically, right? It's just sodium and chlorine. So that actually eliminates a lot of interference that we might have when looking at them using NMR. Really common samples, usually pretty simple fluid inclusions. So the work that I'm doing is kind of preliminary methods research. So as far as geology goes, there isn't a lot of use of NMR spectroscopy. It's mostly reserved for like inorganic chemistry, organic chemistry, stuff like that, pharmaceuticals industry in particular. But as an analytical tool, we don't really use it much in geology. And I think that's usually because it's, as soon as you don't know exactly what you're looking for, things get really crazy really fast. If you look at an NMR spectrum that is not a pure sample, it pretty much just looks like background noise. But so that's kind of why we're focusing now on just really simple minerals, halite and quartz for now, actually, as well.
So I guess, I don't have a background in geology. I do philosophy, but this is really fascinating for me. And I guess I want to know more about, say, the difference between the standard MRI and the kind of MRI you are engaged with, the nuclear MRI. So what's the difference between these two kinds of imaging? And tell us a bit of how these processes actually work and are helpful for your research.
Yeah, for sure. The thing with the difference between MRI and NMR imaging versus spectroscopy is after you run an MRI, like you would if you go to the hospital to get a scan, you actually receive a visible image back that kind of maps where all the radiation is coming from and gives you an overall picture of what's going on. With NMR, the result is basically one single spectrum that's an average of thousands, hundreds of scans, where you just pulse your sample with a certain frequency of, actually, it's in the radio wave frequency. So that's why you have these big shielding capsules around it. If you look up an NMR machine, they're these giant machines, and a lot of that's for shielding and cooling, so you can isolate the sample from any background radiation. But what you do is you're going to pulse a sample, and if you get really down into it, it's like quantum chemistry that honestly I don't fully understand. So simplistically, what you're doing is you're radiating a sample, and that's going to cause a disturbance in the balance between up and down spin with the nuclei, or the nuclei that you're probing. So you're going to pulse it, it's going to create an imbalance, and then they're going to flip back to their natural state. And what that's going to do, it's going to release a very specific wavelength that you can then receive using the same coil that you use to produce the signal. So it's kind of like a back and forth little ping pong. What you're going to do is you're going to ping with your signal, and it's going to hit the sample, and it's going to pong back, and you're going to pick up that signal. And that signal is very, very unique to the chemical environment of the nuclei that you're probing. So the thing with NMR is you can only probe one specific nuclei at a time. So whether that's hydrogen or carbon or sodium, it's dialed in because it's very, very finely tuned to a certain frequency, and there are very, very wide ranges of the frequencies that can be produced or transmitted for each nucleus. So what that lets us do is when we're studying a certain sample, say halite, where it's just sodium and chlorine, if we only want to see the environment around the sodium, we're not going to get any interference at all from any other nuclei that might be in the sample. So
thank you.
Yeah, I hope that helps.
A lot, yes, thank you.
So, pardon this question, but why do we care what's inside the fluid inclusion?
Good, honest question. Yeah, no, I didn't actually really know about fluid inclusions until Robbie approached me in the final months of my 5th year before starting my master's. And she actually proposed that we work with Nigel, the fluid inclusion expert at Western. And what we can do is by evaluating the internal pressure and composition of the fluid inclusions. So how much salt is in it, how much CO2 is dissolved, what pressure was this trapped at, we can kind of back calculate that to the conditions that were there when it was first formed. They're kind of like tiny little time capsules locked away inside the mineral. And since the mineral is so much more robust than, say, doing this with a sample from the Arctic ice for paleoclimates, instead you're looking millions of years in the past at gases and other salts and stuff that are trapped when they were first formed. So what that can do, if you really want to get like bottom line, what can this do for me? A lot of exploration companies can look for mineral traces and specific temperatures and pressures that might be indicative of hydrothermal activity that might deposit a lot of precious metals, or it might give you an indication of where oil and gas reserves might be. And I believe there has been a study on using NMR on fluid inclusions that are rich in hydrocarbons. So there you can actually see and determine what types of hydrocarbons are also trapped within these fluid inclusions. So, yeah.
I was wondering, Stephen, what kind of, what aims do you have that you hope to achieve by the end of your research? Those sort of goals that inform geoscientists. Can you tell us something about your research in those terms?
In terms of my goals,
yes.
We're kind of throwing things against the wall and seeing what sticks right now. It's
amazing.
Very, very hypothetical at this point. We have some preliminary results that we have, like we can see the fluid inclusions contents. We do get signal from fluid inclusions, and there is a discrete chemical shift. So there's a change in the signal based on our pure solvated halite, so our salt water, versus our relatively pure quartz sample. We can actually see a chemical shift based on the sodium sample. So we know something is changing its environment, whether it be pressure, level of salinity, like how concentrated it is, or other interfering ions. We know there's a change, but now we need to understand more systematically how that change happens. So my goal, if I had to pick one that I would want to work, would be to be able to probe the salinity based on the chemical shift.
Cool.
So ideally, you could put a small bit of sample into the NMR, which is about as much as you can put into the NMR at a time. It's very, very small amounts. You put it in there, and from one single NMR scan, you can get the salinity. If we can do that, excellent, because from there, it's a lot more easy. Like it's a lot easier, to try and calculate the pressure, which is normally what you would do with a microthermometry stage, and that can take on the order of weeks to months to do, because you need to take a representative sample of all the fluid inclusions of interest across your sample using a microscope and heating and cooling a stage. So instead of doing all that, the hope would be you put into the NMR, and a few days later, you can have quantitative results.
All right. So you're trying to speed up the process and make it the most efficient way as possible. If you're allowed to say, where are your samples from?
I have some from New Mexico. I have some from South Africa. Planning on getting some from Goderich, I believe. I want to get some from Goderich, so we have some local, like, Southern Ontario samples. I think that would be neat to do. And yeah, no, I think that's it.
Yeah, that was going to be my next question. Do you have any samples from Southern Ontario? Because that would be that'd be interesting to see what the, I mean, everyone talks about how the Michigan and Appalachian basins are shallow inland seas, and that's why we have the salinous salt formation. So it'd be interesting to see how the actual environment was back then, if there was fluid inclusions in there. But
yeah, totally. That's definitely a hope of mine. But as it stands, Nigel's sitting on a wealth of samples from New Mexico, so we're gonna use those as our kind of standard, because they've been pretty well studied. We think we know pretty well what the contents of the fluid inclusions are, and we have a basic understanding of the pressures that are found within the samples. So just as our first samples to do now, as a proof of concept that this is actually a viable thing to do, we're going to start working with those and see where we can go from there.
So Stephen, we live in unprecedented times nowadays. The situation for us graduate students, the more vulnerable people, is a lot worse. And I was just wondering, how has this situation impacted your research? And I'm sure there must be some, I mean, especially for your field. I mean, it's not like you're doing pure mathematics sitting in your kitchen, as some people might be, or doing philosophy, just thinking really hard about stuff. You have to go out in the real world and conduct some experiments and use some machinery as well, perhaps. So I was wondering, how has this impacted your research? And also, what does the future look like for people in your field and in your situation?
Yeah, for sure. No, as far as the whole COVID-19 and self-quarantine, social isolation thing, I think I'd speak for most geologists at this point that a lot of the research has come to a standstill. We are non-essential research, so most of our labs have been shut down. The only access that we are providing is to maintain the machinery that needs to keep working so that the labs are operational when we get back. And unfortunately, I didn't get any new data right before all this rolled in. So I'm kind of trying to get myself working on drafting up my thesis already. Might as well get the literature review written up if I can. But I've had about 4 or 5 hours on the actual NMR spectrometer so far, which is a lot considering, because that is always booked solid. I was hoping this summer, once the undergraduates went away, that there'd be a lot more free time. But again, under the situation, that's not looking so good.
A grad student's dream of uninterrupted time to write their review.
Exactly. But
just a small follow-up. I mean, I see some trees behind you. Where are you?
I'm actually spending some time with my mom right now, isolating up at my cottage. I know everyone said stay at home, but I delivered some groceries. I delivered about 2 weeks of groceries to my mom, so we've been into town once so far in the 3.5 weeks. About 3 weeks that I've been here. So now we're about as isolated as can be.
Hopefully you didn't have any plans to travel to New Mexico for your samples and just, right?
No, we have all the samples we need for now. Yeah, and that's another odd thing about my work being in the field of geology. A lot of the time, like context holds a lot of value for geological samples, but with my work, what I'm trying to do is kind of remove that need for any kind of context to interpret it. As like quantitative samples, I don't need to understand where it came from, because what I'm going to tell you, it shouldn't matter where. I don't know if that really makes as much sense, but I'm mostly looking at the data and trying to compare that to whether it's totally valid, not trying to use it to understand any wider geological systems at this point. So I don't know if I have a lot of field work in my future, but back to what you were asking, Yusuf, about how I think this might change the future for geologists in the field.
Yes.
Honestly, I'm going to say it probably won't change a thing. Geologists are pretty hands-on as a generality, but they like to get out there. They like their field work, and of course, why wouldn't you? And yeah, it's mostly all hands-on work, whether it's on a microscope or in the lab on some kind of spectrometer. But yeah, not a lot of it can be done remotely.
I guess I was also wondering, any plans for doing a doctorate in your field? I mean, maybe it's too early. I mean, I had no idea what I was doing for far too long. I still don't know what I'm doing. I don't know where I can find a job. I'll take it. But what about you? Maybe you have things better thought out.
I wouldn't say I have anything better thought out. I have considered the possibility of a PhD, but at this point, it's kind of way at the back of my mind right now. I've had people tell me, like, when I laid out like my research goals, like what I see the potential in my project right now. A lot of people are saying, like, yeah, there's no way you're getting that done within the scope of a master's. You should do a PhD. And for sure, there's a lot of room to grow with the research that I'm doing, being like such a new field of research. But on the other hand, maybe things don't really pan out that well, or there's a reason that there's nothing published or very little published on this research. So it's all very up in the air.
You could be the world leader in this. You could be the person that creates the first step on the pathway for the future geologists, right?
Well, that's the dream, but not putting too much stock in that just yet.
Of course, you would include field work in that, right? You would make.
Of course, yeah. Then you'd be incorporating the field work.
Of course.
So I sometimes ask this silly question, and sometimes I get answers that are kind of cool. But I was wondering, as someone who's interested in geology and studying mappings of, how we can do imaging of geostructures, is there any particular movie that you like that it's geologists and geochemists in particular are huge fans of? I know we had someone else who was interested in sort of black holes and stuff. So of course we spoke about the Interstellar movie. But I wonder if there's an interesting, cool movie that you can suggest that people can learn a lot about things that we take for maybe granted.
I do not have an answer off the top of my head for that, no.
Okay.
Geologists are often forgotten about, if I can be bold to say that, but they're generally not the first scientists you turn to for a big blockbuster movie.
I know there's a B-roll movie of it's like The Monster Within or something like that. And it was filmed on a rig in Lake Erie back in like the 70s. And they're supposed to be in the middle of Antarctica, and the geologist is saying, oh, everything's going to be fine. And they're taking this like core out, and it's almost like a mixture of like Alien. So you have this alien and like nobody listens to the geologist, nobody listens to the scientist, as every science movie is. They never listen to us. So I think that's the only movie that I've seen that the geologist was totally just forgotten about.
Moving back to a bit of on your research, what are some of the things that have really fascinated you a lot? Was there some sort of discovery that you've made, or a new thing that you didn't know and you realize and you're like, holy smokes, this is amazing. I should tell the whole world and make a movie or something. Have you had any moments like that or anything similar?
One moment that stands out is when I was first learning to do microthermometry, which is kind of the fundamental way of researching fluid inclusions. What you get to do is you have a big can of liquid nitrogen,
Yeah,
and
cool.
you have this little tiny microscope stage where you put your little chip of sample on it, and you look down the microscope and you vary the temperature. So what you get to do is drop it down to -100, -150 degrees Celsius, and you get to watch these little tiny fluids freeze. And you can actually see them like fracture, like as the ice like cracks within it. And then you get to heat it up and watch it all kind of like melt slowly. And you can actually watch the phase changes, which is really cool to do.
What do you mean by phase changes?
Like you get to watch it. Oh, honestly, when I explain it, it doesn't sound very cool, but you get to watch like the little pocket of ice melt. That's not entirely the coolest part, though. The coolest part is when you are trying to reach what's called a homogenization temperature, where all of the fluid inside the inclusion is in the same state. So normally you would have one or two different, maybe three different states inside a fluid inclusion, whether it's a daughter crystal, so like a solid that's crashed out of solution, or you have a gas phase and a liquid phase. What you get to do is you get to heat that up until all of it becomes one single phase. And just before that happens, if you have a pocket of gas, you can start to watch it bounce around as it starts to like get smaller and smaller as more of the gas joins the one more homogeneous fluid. And it actually follows a pseudo-Brownian motion, which, if you know, Brownian motion is actually molecular motion.
Yeah.
So these are so small and they're moving so quickly and heating up enough that they start to simulate that kind of random motion.
Oh, that's
so that
amazing.
Was really cool.
That is really cool. Wow. Thanks for sharing that.
Yeah.
How small are we talking about these fluid inclusions? Like, are we talking like a little tiny, like, a little baby sample of like, how small are we talking when you're looking at these samples?
Yeah, I know you can get fluid inclusion samples that are easily visible to the naked eye. So I think Nigel could show you one that's like on the scale of centimeters. It's a massive one that he has in a piece of halite, or not halite, sorry, quartz, I believe. It's a really large fluid inclusion in quartz, but they can get all the way down to like 20 micrometers in scale, like absolutely minuscule. So
wow.
Yeah, there's a huge range, and it all just depends how they form, whether they've been altered in the course of their geologic history, the mineral, how it expands.
What happens if you drop one?
That's actually a big problem with microthermometry as well. Physical damage, you can crack them, and of course that will alter the internal pressure because the volume changes where the fluid inclusions become. But if you heat them up too much, you can crack them. If you freeze them and they have a certain composition within them, like if there's too much water, then you can crack it that way as well as water expands. So physical damage, yeah, you can destroy a sample pretty easily. Usually with the smaller like fluid inclusion samples, dropping a sample wouldn't be too bad. They're small enough that the shock isn't going to crack open any of the fluid inclusions. So
I guess in your journey all the way from some chemistry, some interest in physics as well, to doing geology and in particular geochemistry, what advice or suggestions can you give to other people who may be figuring things out and maybe have some similar interest? Is there something you can suggest to them that would help them in making their academic decision?
Yeah. It's going to sound cliche, but always keep your mind open, keep your options open. If it wasn't for me taking a geology course in fourth year and getting kind of a taste for what geology actually is, I would have never found this program. I know coming into university, I wasn't even really aware of the geology program. So, I mean, it wasn't for me taking a chance on one elective course, and I wouldn't have found myself here where I am. And I think also it's important to look at what type of work you want to do in the future. So a lot of people are saying like, yeah, I want to go to medical school, I want to be a doctor, but my biggest fear always like coming through school was like, what if I get there and I realize what I'm actually doing day to day is just totally not what I thought it was. But I think it's think more towards where you see yourself wanting to be when you're working, not necessarily what the image of that is.
Yeah.
I know with chemistry, it was a lot of hands-on work, a lot of lab work, which is where I really kind of found the joy in it. I love playing with all the instruments, using all the different equipment, and yeah, that was really fulfilling for me. But I definitely didn't see myself sitting inside on a computer all day. And geology, fantastic as it is, we have all the fieldwork opportunities, right? So look at what you want and try and direct yourself more towards what can actually provide that for you.
You're quite right. I mean, I quite agree that it's so important to keep our options open, and people start doing one field and they go completely left field and they love this new unexplored thing as well. And that has been the experience of so many of us.
Yeah, I know that in geology is definitely one of those things that we're very lucky to be able to study the earth, and we can go out in the field, and there's so many different branches of it. I mean, there's geologists that never leave the office, and that's just, I can't believe that. I don't know why you'd want to stay in an office all day. But we are just about out of time, so thanks so much for coming on Gradcast. If anyone wants to learn about your research, is there anywhere that they could reach you?
Yeah, my university email, spilar, spilar, @uwo.ca. That's always open. If you want to shoot me an email, I'd be happy to get back to you. And social media-wise, I'm not very active there with any kind of content, not just geology, but feel free to take a peek on there if you're really interested.
Just one small thing as well. Could you please show us a bit of the college area as well? I know you showed us a little bit of it, because
show you the view of my window these days.
I just find it very uplifting.
You're on the Canadian Shield?
Whoa!
Oh,
Yeah, I'll start. You gotta.
Wow. Okay.
beautiful.
Yeah.
I was there.
So yeah, that's my social isolation environment right now. Can't complain about.
Cabin in the woods.
Yeah.
Thank you.
So this has been Gradcast, the official radio show and podcast of the Society of Graduate Students at Western University. I've been your host, Reese Patterson.
And I've been your co-host, Yusuf Hassan.
And we've been speaking with Stephen Pilar from the Earth Science Department. This episode was produced by Ariel Frame. If you would like to be involved with the show or get in contact with us, email us at gradcastradio@gmail.com. You can follow us on Instagram, Facebook, or Twitter at Gradcast Radio. To listen to us, we are on the radio at CHRW 94.9 FM. You can also find all of our episodes on our website at gradcast.ca or on podcast apps like Podbean, iTunes, and Spotify. Alternatively, select podcasts have been uploaded to YouTube at Gradcast Radio. Thanks for listening. Have a great night, and